Hi, welcome to this Corbettmaths video. In this video, we're going to look at the video solutions to the area of a segment practice questions. If you need any extra help on finding the area of a segment, if you go to corbettmaths.com/contents and scroll down to video number 63, there's a dedicated video tutorial there on how to find the area of a segment. Alternatively, you could scan this QR code. But in this video, we're going to focus on the video solutions to the practice questions, so let's get started. Okay, let's have a look at question number 1. So question number 1 says, shown below is a sector OAB of a circle with center O. So as you can see, this is a sector of a whole circle. So if you look, there's a circle, and this is a sector, it's a quarter circle. And we're told that AB is a quarter of the circle. So that makes sense because A and B are points on the circumference, and the line joining them is a chord. So that's the chord of the circle. And we've been asked to work out the area of the shaded segment. So this green region is a segment because it's the area bounded by an arc and a chord. So that's a segment. And we've been asked to work out the area of that segment. Now to do that, what we're going to do is we're going to work at the area of the sector, which is the quarter circle, the area of the quarter circle, and then we're going to find the area of the triangle and take the area of the triangle away from the area of the quarter circle, and what's left will be the area of the segment, this green region. So let's do that. Let's start off with the sector to begin with. So let's find the area of this sector, this whole sector OAB. So it's a quarter circle, so we can do it in a couple of different ways. We could do 90, because it's 90 degrees, over 360, multiplied by pi r squared. Alternatively, we could just find the area of the whole circle and divide it by 4, and that's what I'm going to do. So the area of the whole circle would be pi times. Now, if we've got the whole circle, the radius would be 12, so pi times 12 squared would be the area of the whole circle. And pi times 12 squared would be equal to 144 pi centimeters squared, or if you wanted to work as a decimal, it would be equal to 452.389 and so on centimeters squared. So that's the whole circle. But we just want to find the area of this sector, this quarter circle, so we're going to divide it by 4. So we're going to write down either 144 pi divided by 4 or 452.389 and so on divided by 4. I'm going to do 144 pi divided by 4 just because it's a bit easier to write down. And whenever I do 144 pi divided by 4, that's equal to 36 pi. So that means the area of this whole sector is 36 pi centimeters squared, or as a decimal number be equal to 113.09733 and so on centimeters squared. So that's the area of the sector. Now what I want to do is I want to find the area of the triangle, because that's what we're going to take away to see what's left, which would be the area of the segment. So let's then write down here triangle, so the triangle. So as you can see, we've got this triangle, and to find the area of a triangle, we do half the base times the height for a triangle like this, because we've got the base and the perpendicular height. So we can just do half the base times the height. So half the base times the height is the area. The base is 12 and the height is 12, so we're going to do half of 12 times 12. And a half of 12 is equal to 6, and then we're going to multiply that by 12, and 6 times 12 is 72 centimeters squared. So the area of this triangle is 72 centimeters squared. And we want to find the area of this segment, this green region. So if we take the area of the triangle away from the area of the sector, we'll find the area of this segment, this green region. So let's do that. So let's write down our 36 pi, which is the area of the sector. Now we could have written down 113.09 and so on, and that would be the same answer. So 36 pi, take away 72 and see what we get. So whenever we do 36 pi, take away 72, that's equal to 41.097335553 and so on centimeters squared, and that's the area of this segment. Now at this point we could have done 113.09733 and so on, take away 72, and we get the same answer, and that's it. So let's write our answer down. The answer is equal to 41.097 centimeters squared to 3 decimal places, and that's it. Okay, let's have a look at question number 2. So question number 2 says, shown below is a sector OAB. So we've got OAB, and that's a sector of a circle with center O. So we've got this whole circle, and this is a sector of the circle, and we've got an angle of 120 degrees. That means that this sector is a third of a circle, because 3 120s is 360. So this is a third of a circle, and we're told that AB is a chord of the circle. So AB, the line joining A and B, is a chord. So A and B are points on the circumference, and that's the chord, the straight line joining them. And that means this green region is a segment, because that's the arc and that's the chord, so that means that that's a segment. And we've been asked to work out the area of this shaded segment. So to find the area of this segment, we're going to find the area of the whole sector, we're going to find the area of the triangle, and we're going to take them away to find the area of the segment. So let's start off by finding the area of the sector. So let's write that down, sector. So for the sector, now in terms of the sector, we could do pi r squared for the whole circle and then divide it by 3 because it's a third of a circle. Alternatively, we could use the formula. The formula for finding the area of a sector would be beta over 360 multiplied by pi multiplied by the radius squared. And what that means is we're putting the angle, this 120 over 360, so that gives us the fraction of a circle, and if we simplify that, that's a third, multiplied by pi r squared, which is the area of the circle, so a third multiplied by the area of the circle, and that's it. So let's work out the area of the sector. So theta is the angle, which would be 120 degrees, over 360, multiplied by pi and multiplied by the radius of the whole circle, which is 5 squared. And now if we work this out, we get the area of the sector, which would be equal to 25 over 3 pi, or 26.179938 and so on centimeters squared. So that's the area of the whole sector. Now let's find the area of the triangle. Now with this triangle, we've got two sides and the angle in between them, so we're going to use a half AB sine C to find the area of this triangle. So let's write that down, the triangle, and we're going to use a half AB sine C. So the area of a triangle is found by half AB sine C, where A and B are two sides and C is the angle in between them. So it's going to be a half multiplied by A, which is 5, multiplied by B, which is 5, and it doesn't matter which way around we do those, multiplied by the sine of the angle, so that's going to be sine 120. And whenever we type in our calculator, a half times 5 times 5 times sine 120, that's equal to 25 root 3 over 4, or alternatively 10.82531755 and so on centimeters squared. So that's the area of the triangle. So we now know the area of the whole sector, we now know the area of the triangle, so if we take them away, we'll find the area of the segment. So let's do that. So 26.179938 and so on, subtract 10.82531755 and so on. And whenever we do that, we get an answer off. And it can be quite useful in these questions to actually store these in your memory, in your calculator. So storing this answer in your memory and storing this answer in your memory so that you're not rounding them, and you can actually use the full versions of them whenever you're doing the subtraction. But whenever we do that, we get an answer of 15.35462123 and so on centimeters squared. So that's the area of the segment. And the question says work out the area of the shaded segment and give your answer to one decimal place. So we need to round this to one decimal place. Our answer would be 15.4 centimeters squared. And that's it. Okay, let's have a look at question number 3. So question number 3 says we've got a sector of a circle and the radius of the circle is 10 centimeters. We're told that ABC is the arc of the circle and AC is the chord, so this is a segment in green. And we're told the angle AOC is 30 degrees and to calculate the area of the shaded segment. So we need to find the area of this green region. So let's get the area of the sector and then we'll find the area of the triangle and take them away, and what's left will be the area of the segment. So let's do that. So let's start off with the sector. So the sector. So the area of the sector will be theta over 360 multiplied by pi multiplied by the radius squared. So we're going to do 30 over 360 multiplied by pi multiplied by the radius, which is 10 squared. And then we'll work out what this is, and it's equal to 26.1799 and so on centimeters squared. So that's the area of the sector. Now we need to find the area of the triangle. So let's find the area of this triangle, and to find the area of the triangle we're going to use a half AB sine C. So we'll use a half AB sine C, where A and B are the two sides, 10 and 10, and C is the angle between them, which is 30 degrees. So we're going to do a half multiplied by 10 multiplied by 10 multiplied by the sine of the angle in between them, so that's the sine of 30 degrees. And whenever we work out a half times 10 times 10 times sine of 30 degrees, that's equal to 25. So that means that the area of this triangle is 25 centimeters squared. So we've now got the area of the sector, which is 26.1799 and so on. So that's the area of the whole thing. We know the area of this white region, this triangle, is 25 centimeters squared. So if we take the area of the triangle away from the whole thing, that'll tell us the area of this green region. So let's do that. 26.1799 and so on. Take away 25 is equal to 1.1799 and so on. So that means the area of this segment is equal to 1.1799 and so on centimeters squared. Well, let's round it to two decimal places, so that'll be 1.18 centimeters squared. And that's the area of this shaded segment. Okay, let's have a look at question number 4. So question number 4, we've got a sector and we're told that PQR is the arc of the circle, centre O, with radius 6 centimetres. And we're told that PQ is the chord of the circle, so that means that this green region is a segment. And we're told the angle POR is 25 degrees. And we've been asked to work out the area of this shaded region here. So we need to find the area of the segment. So let's get the area of the sector, then we'll find the area of the triangle and take them away, and what's left will be the area of the segment. So let's do that. So let's start off with the sector. So the sector. So for the sector, the formula is theta over 360 multiplied by pi multiplied by the radius squared. So let's substitute in our values for theta, which is 25. So 25 over 360 multiplied by pi multiplied by the radius squared, which is 6 squared. And whenever we work that out, we get that's equal to 5 over 2 pi, or as a decimal number, 7.853981634 centimeters squared. So the area of this whole sector is 5 over 2 pi, or 2.5 pi, or 7.85 and so on centimeters squared. So we've now got the area of the whole sector. Now let's find the area of the triangle. So for the triangle, we've got this triangle here, which is POR, and we've got two sides and the angle in between them, so we can use a half AB sine C, a half AB sine C. So we've got the two sides A and B, so they're 6 and 6, and we've got the angle between them, which is 25 degrees. So that'll be a half times 6 times 6 times the sine of 25 degrees. And whenever we do that, we get that's equal to 7.607128711 and so on centimeters squared. So we've now got the area of the triangle and we've got the area of the whole sector. So if we take them away, we'll find the area of the segment. So let's do that. So that would be 7.85398 and so on. Subtract 7.6071288 and so on. And whenever we do that subtraction, we get an answer of 0.24685845521 centimeters squared. So that's the area of this segment. Now we need to give our answer to 4 significant figures. Now because it's a 0 point number, the 0 is not going to be significant, so we're going to start looking at these digits being significant. So we've got 1, 2, 3, 4. So we want to round it to 4 significant figures. Now because the next digit, the 5th significant figure, is a 5, that means we're going to round up. So our answer would be 0.2469. So that, and centimeters squared. So the area of this segment will be 0.2469 centimeters squared. And that's it. Okay, let's have a look at question number 5. So question number 5, we've got this circle, and we're told that BC is a chord of the circle. So BC is a chord, so it's a straight line joining 2 points on the circumference of the circle. And we've got the center O, and it's got a radius of 9 centimeters. So OB is 9 centimeters, and BC is equal to 10 centimeters. And we've been asked to calculate the area of this shaded segment. So we need to find the area of this shaded segment. So we've got this segment here. Now the first thing I'm going to do in this question is, I'm going to draw the radius from O to C, the other radius there. So now that I've drawn that over radius, and because OB is equal to 9 centimeters, OC would also be equal to 9 centimeters. And now that I've drawn the over radius, so I can see here we've got our sector and we've got our triangle. And if we can find the area of the sector and find the area of the triangle, we can take them away to see what's left for the area of the segment. Now to find the area of the sector, it would be really important to know the size of this angle. So we need to find the size of that angle. Now to find the size of this angle, there's a couple of approaches we could use. We've got a triangle OBC, and we know 3 of the sides. So we've got the OB is equal to 9, we've got the BC is equal to 10, and we've got OC is equal to 9. So that means we could use the cosine rule, because we've got a triangle, and if we know 3 sides of the triangle, we can use the cosine rule to work out the size of one of the angles. So that's one option, is to use the cosine rule. Or another approach we could use is to use basic trigonometry, and that's the approach that I'm going to use. I'm actually going to cut this triangle in half. I'm going to go straight across here, and I'm going to cut the triangle in half. Now that means that because it was an isosceles triangle, that line is going to be a line of symmetry when we cut it in half that way. So because the line BC was equal to 10 centimeters, it will now be 5 centimeters there and 5 centimeters there, and that's a right angle. Now we've got 2 smaller triangles. We can work out the size of this angle here, and I'm going to call this angle Y. And if we find the size of angle Y, if we double it, then that'll be the size of angle beta. So let's find the size of angle Y using basic trigonometry. So we've got Y, that means that 5 is the opposite, and it means that 9 is the hypotenuse because it's opposite the right angles, that's the hypotenuse. So we've got the opposite and hypotenuse, so that's going to be sine. Sine Y is equal to the opposite over the hypotenuse. So that means that sine Y is equal to the opposite, which is 5, over the hypotenuse, which is 9. So sine Y is equal to 5/9. This angle is obviously not equal to 5/9, so we need to do the inverse sine. So we're going to do the inverse sine. Y is going to be equal to the inverse sine of 5/9. And if we do shift sine on our calculator, so press shift sine and then type in 5/9 and press equals, that gives us that Y is equal to 33.7489 and so on degrees. Now that's the size of angle Y. We want to double it to find beta, so that means that beta will be equal to, if we multiply this by 2, so 2 times 33.7489 and so on, we'll find beta. So if we multiply by 2, we get that's equal to 67.49797719 degrees. So that's the size of this angle beta. So I'm actually just going to move this away for the minute, just so we can see it a bit better. So that means this angle theta is equal to 67.4979 and so on degrees. So we've just replaced theta with what it is, which is 67.4979 and so on degrees. Now it's important whenever you're doing this question that you leave your working on. I'm just sort of clearing it so that you can see what I'm doing in this explanation. So we've now got this sector. So we've got the sector OBC. And if we can find the area of the sector and then find the area of the triangle and take them away, we can then see the area of the segment. So let's deal with the sector to begin with. So the sector. So the area of the sector is theta over 360 multiplied by pi multiplied by the radius squared. So theta will be 67.4979 and so on over 360 multiplied by pi and multiplied by the radius of the circle, which is 9 squared. And whenever we work that out, we get that's equal to 47.7115 and so on centimeters squared. So that's the area of the sector. Now we need to find the area of the triangle. So let's write that down, triangle. So for this triangle, you can see we've got two sides, the OB and the OC, and we know the angle in between them. So we can use a half AB sine C, a half AB sine C. So it's going to be a half multiplied by A, well, let's call that 9 centimeters, multiplied by the other side, which would be 9 centimeters, multiplied by the sine of the angle in between those, which is 67.4979 and so on. And whenever we work that out, we get that's equal to 37.41657 and so on centimeters squared. So we've now got the area of the sector, which is 47.711 and so on. We've got the area of the triangle, which is 37.416 and so on. And if we take them away, we can then find the area of the segment. So let's do that. And that's equal to 10.2949 and so on centimeters squared. And let's just round this to 3 decimal places. So our answer would be that the area of this segment would be 10.295 centimeters squared. And that's it. And just remember in this question, you could have used the cosine rule to find the size of this angle. I used basic trigonometry, but either approach is fine. Okay, let's have a look at our next question. Okay, let's have a look at question number 6. So question number 6 says the diagram shows triangle OAB and arc AB of a circle whose centre is O and his radius is 20 centimetres. And we've been asked to work out the size of this angle theta. So we need to find the size of this angle theta. Now there's a couple of ways we can do this. Just like our last question, we could either use the cosine rule because we've got a triangle OAB. So we know the length of OA is 20. We know the length of AB is equal to 28. We know the length of BO or OB is equal to 20. So it means we can use the cosine rule to work out the size of this angle, because if you've got a triangle and you know 3 of the sides, you can use the cosine rule to work out the size of the angle. Alternatively, we could use basic trigonometry, and that's the approach I'm going to use. So I'm going to just cut this in half like so. Just cut it in half. It was an isosceles triangle, so that means that it will be a right angle there, and it will be 14 centimeters above, half of the 28, and 14 centimeters below. And we've now got a right angle triangle. And the angle here will be, instead of being theta, it will be, let's call it y, and that'll be half of theta. So whenever we find y, we can double it to find the size of theta. So if we have a look at y, this segment is the opposite, and that this is a right angle, so that will be the hypotenuse. So because we're dealing with the opposite and hypotenuse, that means we're going to be dealing with sine. So sine y is equal to the opposite over hypotenuse. Some people remember SOHCAHTOA, or I remember Two Old Angels Skipped Over Heaven. So we've got skipped over heaven, the SOH. And then that means that we can then find out what y is. So the sine of y is equal to the opposite, which is 14. Sine y is equal to 14 over the hypotenuse, which is 20. So we've now got the sine of y is equal to 14 over 20. Well, this angle is obviously not 14/20ths. So we now need to do the inverse sine. So we're going to do the inverse sine of 14/20ths. And that will give us y. That gives us that y is equal to 44.427004 degrees. Now that's why we wanted to find the size of theta. So that's going to be, because we halved the triangle, that's going to be double that angle. So we're going to do 2 times 44.427004. And when we multiply that by 2, that's equal to 88.854008 degrees. And let's write that down, 88.854 degrees. Okay, let's have a look at part B. Part B says find the length of arc AB. So we want to find the length of the arc AB. So this time we want to find the length of an arc. So the formula to find the length of an arc will be theta over 360 times pi. Now instead of using pi r squared, which is the area of the circle, we're doing the fraction of the circumference. So it's going to be pi times diameter, or some people use 2 pi r there instead. So 2 times pi times the radius. I tend to use pi times diameter. It's really up to you. So here we've got theta. Now theta is the angle. triangle, if we go back up to our question, we want to find the length of this arc AB. So it's going to be beta over 360. Now beta is 88.854. So we're going to do 88.854 over 360 times by pi and times by the diameter of the whole circle. So if we go back up, the diameter of the whole circle would be 40 because the radius is 20, so the diameter would be 40. So multiply by 40. And whenever we work that out, we get that's equal to 31.015899 and so on centimeters. Or let's just round that to 3 decimal places, so that'll be 31.016 centimeters. And because it's the length of an arc, that's in centimeters. And then part C says find the area of the shaded segment to the nearest centimetre squared, or the nearest square centimetre. So we want to find the area of the shaded segment, so we're going to find the area of the sector, we're going to find the area of the triangle, and we're going to take them away to find the area of the segment. And then we're going to round that to the nearest 1 centimetre squared, or nearest squared centimetre. So let's do that. So let's find the area of the sector, so that's going to be beta over 360 times by pi times by the radius, which is 20 squared. So let's do that. So the sector, 88.854 over 360 multiplied by pi multiplied by the radius, which is 20 squared. And whenever we do that, we get the area of the sector. And that's equal to 310.1589986 and so on centimetres squared. So that's the area of the sector. And we need to find the area of the triangle. So we're going to be using a half AB sine C, half AB sine C. So that's the two sides and the angle in between them. So if we go back up, if we have a look at this triangle, we want to find the area of this triangle. So we're going to do half AB sine C. So the two sides, the 20 and the 20, the two radii, 20 times 20, times by the sine of the angle. So it's going to be a half times 20 times 20 times the sine of 88.854 and so on degrees. And whenever we do that, we get an answer of 199.959996 centimetres squared. So we've got the area of the sector, we've got the area of the triangle. If we take them away, that'll be the area of the segment. So for the segment, we're going to do 310.1589 and so on, subtract 199.959 and so on, and see what we get. So whenever we do our subtraction, we get 110.19 and so on centimetres squared. Now we've been asked to give our answer to the nearest centimetre squared, or the nearest square centimetre. So to the nearest square centimetre, that would be 110. So answer is 110 centimetres squared. Okay, let's have a look at our next question. So question number 7, we've got this sector OAB, and we know that OA, so OA is the radius of the circle, and that's equal to 9 centimetres, and we've got the arc AB is equal to 10 centimetres. And we've been asked to find the size of angle AOB, so we want to find the size of this angle. Let's call it beta. So we want to find the size of that angle. Now, the good thing in this question is we know the arc length, so let's use that to help us work out the size of this angle. So to find the arc, we would normally do beta over 360 multiplied by pi multiplied by the diameter. Remember, it's the fraction of the circumference, so pi times diameter, and that would give us the arc length. Now in this case, we know that's equal to 10, so that's equal to 10. Now we don't know beta, so we've got beta over 360 multiplied by pi multiplied by the diameter. Now the diameter of the whole circle, and if the radius is 9, the diameter of the whole circle would be equal to 18, and that's equal to 10. And now we can solve this to find the size of beta. So let's divide both sides of the equation first of all by 18. So let's divide by 18 and divide by 18. So we would get beta over 360 multiplied by pi. We divide by 18 to get rid of the times by 18, and that would be equal to 10 divided by 18 is equal to 5/9. So that's 5/9 on this side. We now want to get rid of the pi, so we're going to divide both sides by pi and divide by pi. The left hand side would just be beta over 360. And then on the right hand side we had 5/9, so we're dividing by pi, so divide by pi, and that's equal to, it'd either be 5 over 9 pi, or as a decimal number 0.176838 and so on. And I'm just going to leave that on my calculator display. Now we don't want beta divided by 360, so let's times by 360 and times by 360, and we'll get the beta is equal to, and if we just press, we've already got this on our calculator display, if we just press times 360, that's equal to 63.66197724 degrees, and that's the size of beta. So beta is 63.662 degrees to 3 decimal places, and I've just rounded that. But I'm actually going to save this in my memory book, in my calculator, this full answer, because it might be useful for later questions. So I'm just going to press store A, so it's now stored in as letter A in my calculator. Okay, part B. Part B says find the area of the shaded segment. So we need to find the area of this segment here. So we want to find the area of the sector, we want to find the area of the triangle, and then we can then work out the area of the segment by taking them away. So let's find the area of the sector. So sector. So for the sector, it's β over 360 multiplied by pi multiplied by the radius squared, the fraction of the area of the whole circle. So that's going to be 63.6619 and so on, divided by 360, multiplied by pi multiplied by the radius of the circle squared. So that's going to be 9 squared. So 9 squared. And whenever we do that, we get an answer off. Now I'm going to use my letter A, so recall A, divided by 360 multiplied by pi multiplied by 9 squared. And whenever I do that, I get an answer of 45. So that means that the area of the sector is 45 centimeters squared. And that's great. So if you used a rounded version, you might not have got a nice answer such as 45 centimeters squared. So it's always quite good if you can to use the, save things into your memory, such as the angle β, so that whenever you're doing further calculations that you get as accurate a version as you can of the answer. Okay, so we've got the area of the sector, which is 45 centimeters squared. Now we need to find the area of the triangle. So we've got 9, this is 9 as well, 9 centimeters and 9 centimeters, and we've got the angle between them, so we can do a half AB sine C. So let's do that. So for the triangle, that's going to be a half AB sine C. So it's going to be a half multiplied by A, which is 9, multiplied by B, which is 9, multiplied by the sine of the angle, which is 63.6619 and so on. Or my calculator, I'm going to press 0.5 multiplied by 9, multiplied by 9, multiplied by the sine, and then I'm going to recall A. So I'm using the full calculator display for that. And whenever I do that, I get an answer of that's equal to 36.29578 and so on centimeters squared. So now I found the area of the sector, and we've got the area of the triangle. We can take them away to find the area of the segment. So 45 subtract 36.29578 and so on is equal to, so 45 take away answer is equal to 8.7042158858 and so on centimeters squared. And let's just round that to 3 decimal places. That'll be 8.704 centimeters squared. And that's it. Okay, let's have a look at our last question, question number 8. So question number 8 says, shown below are 2 circles which have got centres A and B. So we've got this circle with centre A, and we've got this circle with centre B. And the radius of each circle is 9 centimetres. So that means that the radius of each circle is 9 centimetres. We're told that AB is equal to 9 centimetres, so that means that AB, that distance is 9 centimetres as well. And that actually makes sense because, as you can see, if we've got the circle A, B's on its circumference, and we know the radius is equal to 9 centimetres, so that's 9 centimetres. And we've been asked to work out the area of the shaded region, so we want to find the area of this whole shaded region, the sort of the area of that overlap. Now to begin, I'm actually just going to get rid of that line to begin with. I'm actually going to draw this line on our diagram, the line going down here. And I'm going to just talk about the approach that we're going to use. So to find the area of this green region, what I'm going to do is I'm actually going to find the area of this region to begin with, this region here. And to find the area of this region, what I'm going to do is I'm going to consider, here we've got a triangle, there and there. And then we've got, if we look at it, we've got a sector. And then we've got a triangle, and if we find the area of the whole sector, so going around this sector here, and if we find the area of the triangle, if we take them away, we can then find the area of this segment. Once we find the area of this segment, we can just double it, we can multiply by 2, and then that will give us the area of the whole green region, the whole shaded region. So what we need to do is find the area of this segment here. Okay. Now, before we do that, we actually need to find the size of this angle. Now, what's great here is actually in this question, we know the radius of each circle is 9 centimeters. So if we look at this triangle here, we have got that's 9 centimeters from A up to this point. Let's call this point M, and let's call this point N. So this line from A to M has got a length of 9 centimeters, and from A to N would be 9 centimeters. Now, if we go back to what we were told in the question, we were told that AB is 9 centimeters. So if I draw the line from A to B, this line here, we know that's 9 centimeters. Now, what's great is that means that because this line MN goes straight down through the middle, that would be 4.5 centimeters on that side, and that's a right angle, and that's 4.5 centimeters. So we've now got a right angle triangle, and we want to find the size of this angle. So if we use trigonometry, we can find the size of this angle here. Let's call it Y. And then we can double it to find the size of the whole angle, and then we can use our approach we just talked about. So let's actually sketch that triangle out to the side here. So we've got A, we've got M, and we've got this point here. Let's just call it P for the minute, okay? So P's in the middle of A and B. It's the midpoint of AB. So let's call it P. And that's a right angle triangle. And we really want to find the size of this angle. Let's call it Y. And we know that AM is equal to 9 centimeters. And we know that from A to P to the middle is equal to 4.5 centimeters. So if we can work out the size of this angle, then we can double it to find the size of the whole thing. So let's find Y. So this will be the hypotenuse because it's opposite the right angle. This side would be the opposite. Now we're not using that in this question, and we've got here the adjacent. So we're looking for the trigonometric ratio which uses the adjacent and the hypotenuse. So soc ca toa, that's your ca, or your two old angels skipped over heaven carrying a harp, a harp. So we've got the cos of Y is equal to the adjacent over hypotenuse. And that's equal to the cos of Y, the adjacent is 4.5. The hypotenuse was equal to 9, so we've got 4.5 over 9. And if we do, Y is equal to the inverse cos of 4.5 over 9, that would give us Y is equal to, and whenever we work out the inverse cos of 4.5 over 9, or a half, and the inverse cos of a half would be 60 degrees. Or in your calculator, if you test shift cos of 0.5, you get 60 degrees. So that means that Y is 60 degrees. So that means that this is a 60-degree angle. So that means that half of the angle is 60 degrees. So it means the whole angle would be equal to 120 degrees. So let's actually just get rid of this line in the middle for the minute. So let's get rid of that, and let's get rid of our Y, and let's get rid of the line joining AB. We now know that this angle in here, this angle is 120 degrees, this angle here. So that's fantastic. Now we know this angle is 120 degrees. We can find the area of the sector, the whole sector, AMN. We can find the area of that sector. And then we can find the area of the triangle, AMN, and then take them away to find the area of this bit, and then we can double it to find the area of the whole thing. So let's do the sector to begin with. So the sector. So the area of the sector will be equal to veta over 360. So in this case, it's 120 over 360, multiplied by pi times by the radius squared. And the radius is 9, so 9 squared. And whenever we work that out, we get that's equal to 27 pi, so 27 pi centimeters squared, or as a decimal number, it would be equal to 84.823 and so on centimeters squared. So that's the area of the whole sector, so AMM, this part here, this sector here. Now what we're going to do is work at the area of the triangle, AMN, and then that's going to be then the area of this triangle, and then we'll take them away. So let's do the triangle. Let's do it up here, triangle. So for the triangle, we know the two sides, which are the radii, 9 centimeters and 9 centimeters, and we've got the angle between them. So it's going to be half times 9 times 9 times sine of 120. And that's equal to 81 times root 3 over 4, or 35.074 and so on centimeters squared. So we now know the area of this sector, AMN, and we know the area of the triangle, AMN. And if we take them away, we'll get this shaded region here, this shaded region in here. Okay, so if we do our 84.823 and so on, take away 35.074 and so on, that's the area of the shaded region, and that's equal to 49.74897 and so on centimeters squared. So that's the area of this shaded region, and that's half of the area of the whole region. So if we double it, that'll then be the area of the green area, the area of the whole shaded region. So let's do that. So let's take our 49.74897 and so on, and multiply that by 2, and that's equal to 99.4979 and so on centimeters squared. And let's just round our answer. Let's round our answer to 3 decimal places. It's going to be 99.498 centimeters squared. And that's it. So these have been the video solutions to the area for segment practice questions. I really hope you found this video useful. If you have found it useful, please like it and please subscribe to the YouTube channel. If you do need any extra help on the area for segment, if you go to Corbettmaths.com and scroll down to video number 63, there's a video tutorial there which would be useful for you. Also for this topic, it might have been useful to make sure that you know the cosine rule, the area for triangle using a half AB sine C, the area for a segment, the arc length formula as well. Those videos might be useful as well. But I really hope you found this video useful. Thanks so much. Cheers. Bye.